Friends, today we will continue with the study of small signal stability. Last time we have included the field flux dynamics in the small perturbation model which we developed. We have also seen that due to change in change in field flux, that is delta psi f d, the electrical torque produced delta T E, the delta of T E, that is the change in electrical torque or air gap torque. That is, if you find out this transfer function relating the incremental change in air gap torque to incremental change in angle, then this transfer function comes out to be equal to minus k 2 k 3 k 4 divided by 1 plus S T 3. Now, we have also seen last time that in case we analyze the performance under steady state conditions, that is when S tends to 0, right, then the incremental change in air gap torque is given by this equation delta T E is equal to minus k 2 k 3 k 4 delta delta. Okay. Now, if you look carefully here in this transfer function block diagram which we had developed last time, that delta T E, which is the net deviation in the electrical torque, is now sum of the two components, one produced due to this constant k 1, that is k 1 delta delta, and another produced due to change in field flux linkages, that is k 2 delta psi f d. Okay. Now, under steady state condition we can see here actually that the total change in torque or air gap torque will be equal to k 1 minus k 2 k 3 k 4 minus k 2 k 3 k 4 into delta delta, right. Now, the net effect is that the synchronizing torque coefficient, when we assume the field flux linkage is constant, right, is more than when you consider the change in field flux linkages, right. That is, the change in field flux linkages takes place basically due to the demagnetization effect, okay. And the steady state stability limit is reached when we have this condition satisfied, that is k 1 is equal to k 2 k 3 k 4. That is when this product k 2 k 3 k 4 is equal to k 1, right, then the net synchronizing torque coefficient becomes 0, okay, and that is the steady state stability limit. Now, we shall examine the case when the rotor of the synchronous machine is oscillating with some frequency. That is, we examine a case where rotor of the synchronous generator is oscillating at some frequency, at rotor oscillation frequency. Now, to analyze this, we again take the same transfer function delta T divided by delta delta, right. This is equal to minus k 2 k 3 k 4 or 1 plus S times T 3. Okay. Now, we will not set S equal to 0. Okay. You multiply this numerator and denominator by a term 1 minus S T 3. Okay. This is to rationalize. We will get the expression for this transfer function as minus k 2 k 3 k 4 into 1 minus S T S T 3 divided by 1 minus S square T 3 square. Now, this expression can be written in this form, that is delta T due to change in field flux linkages only, okay. That is equal to minus k 2 k 3 k 4 divided by 1 minus S square T 3 square into delta delta. Now, when you multiply this second term becomes plus again, plus k 2 k 3 k 4 T 3 K2, K4, K2, K3, K4, T3 divided by the same term, that is 1 minus S square T square into S delta delta, into S delta delta. Okay. Now, in this expression we will set S equal to j omega, that is you substitute S equal to j omega, where omega is the frequency of rotor oscillations. Omega is the frequency of rotor oscillations, and we also substitute here delta delta equal to omega naught by S delta omega r. Okay. Where delta omega r is the deviation in rotor speed with respect to synchronous speed. Therefore, if you make these two substitutions in this equation, right, you can easily see that S delta delta is equal to omega naught into delta omega r, right. And this term is, when you put S equal to j omega, this comes out to be real term, right, because K2, K3, K4 are constants. 1 minus S square T3 square will become 1 plus omega square T3 square. Okay. S equal to j omega, square of this is equal to minus omega square, and therefore, it becomes plus. Okay. Now, here when I am putting here S equal to j omega here, but one thing we can observe very carefully here is that before I substitute the value of delta delta, right. If you see in this equation, if I substitute S equal to j omega, then this term can be characterized as synchronizing torque component, because this is because of this coefficient multiplied by delta delta. Therefore, this term is in phase with speed is in phase with change in rotor angle. Okay. While when you see this term, it will come out to be in quadrature with rotor angle. Okay. And when we make this substitution in this equation, the change in electrical torque or air gap torque due to change in flux linkages only is written as Ks is a function of delta psi f d. I am writing this Ks is not a product, it is not a multiplication, that Ks is a synchronizing torque coefficient due to delta psi f d only into delta delta, plus Kd due to delta psi f d, that is the damping torque coefficient due to variation in field flux linkages only, right, multiplied by omega naught into delta omega r. Now, when we can see very carefully here that this term represents the synchronizing torque component, because when I multiply this to take the complete term, then when I take the complete term, it becomes the synchronizing torque component. When I take this term completely, it becomes damping torque component. Now, if I take the coefficient of delta delta, then this portion becomes synchronizing torque coefficient, and this portion of the expression will become damping torque coefficient, right. Now, to understand this thing more carefully or more clearly, we take an example where for a particular operating condition, the K1 is 0.7642, K2 is 0.8649, K3 is equal to 0.323, K4 is 1.4817, T3 is 2.365. Okay. We take a specific rotor oscillation frequency, that is rotor oscillation frequency is taken as 6.41 radians per second, electrical radians per second. Now, with these parameters, okay, assumed, with this constant assumed, right, when we substitute in this expression for delta t as a function of delta psi f d, delta t produced by delta psi f d only. If you substitute in this expression, then the synchronizing torque coefficient due to variation in field flux linkages comes out to be minus 0.00172 and damping torque coefficient comes out to be 1.53, right. Now, here we can we have to very carefully understand that these two terms which you have computed here, they are function of these K1 to K4 parameters or K1 to K4 constants, T3 and the rotor oscillation frequency. Okay. Therefore, as the operating condition changes, you will find actually that this K1 to K4 constants will vary, T3 will also vary, right. This rotor oscillation frequency also varies, and therefore, the synchronizing and damping torque coefficients contributed by demagnetizing effect will also vary. But one conclusion which we draw is that when the rotor is not in steady state condition or when the rotor is oscillating with some frequency, right, it contributes to negative synchronizing torque coefficient and it contributes to positive damping torque. Okay. This is a very important conclusion which we should always keep in our mind. Now, further we want to see the what is the total synchronizing torque coefficient, then this total will come out to be equal to K1 plus Ks produced or contributed by variation in field flux linkage. That is, Ks is the net synchronizing torque coefficient. This will be equal to K1 plus the synchronizing torque coefficient contributed due to field flux variations or field flux dynamics. Okay. Now, particularly in this case, the value of K1 is 0.7642 and the second component is minus 0.00172. Okay. And one can find out the resultant, that will be 8, how much? 6, okay. 1, 2, 3, 4, 5, okay. This is 8 goes, it will be 4 here, 2, 6, 7, that is 0.76248. In fact, the decrease in synchronizing torque coefficient is not very significant, it is a very small decrease. Okay. This is what is the message, or this is the conclusion which we draw from this. Okay. Now, in all these studies which we have reported till now, we have assumed the you can see this in this diagram. In this diagram, this is our transfer function model which we had developed. This delta EFD was set equal to 0. The meaning of setting delta EFD equal to 0 is the constant field flux, constant field voltage condition. That is, the field voltage applied is constant, delta EFD is 0, it means EFD is constant. Okay. Now we will include the effect of excitation system. We will include the effect of excitation system in our model. Now, to include the effect of excitation system in our model, let us start with the terminal voltage condition, because to the exciter or excitation system, right, at the summing point we give input signal that is corresponding to the terminal voltage of the synchronous generator. Let us start from the terminal voltage. The terminal voltage is written in terms of D and Q axis component as E d plus j times E q. Okay. Then we can write down E t square equal to E d square plus E q square. Now, what we do is that we give small perturbation to these variables, that is E t, E d and E q. Let us assume that E t is perturbed and the perturbed value is or the increment is delta E t. Similarly, E d increment is delta E d and increment of E q is delta E q. When you make this perturbation, we can write the equation in this form. E t o is the steady state voltage, okay, and E t o plus delta E t is the terminal voltage. Okay. Therefore, the perturbation is around this voltage E t o. Therefore, E t o plus delta E t square equal to E d o plus delta E d square, okay, plus E q o plus delta E q square. This is a very straightforward and simple expression. Now, what we do is that we expand this equation, we just expand it and neglect the second order terms in terms of perturbed values. Second order terms which are involving the perturbed values, that is we will ignore delta E t square, similarly delta E d square, delta E q square, because they are small and square will be negligible. If you make that assumption, then we can write down this equation as E t o delta E t equal to E d o delta E d plus E q o delta E q. Okay. Because E t o square is equal to E d o square plus E q o square, right. Therefore, these terms will vanish from the resulting equation. Okay. So, that now we can write down delta E t, the change in terminal voltage as E d o divided by E t o delta E d plus E q o divided by E t o delta E q. Okay. Now, at this stage our problem is that this delta E d and delta E q, these are not the state variables, these are not the state variables, right, and therefore, we have to eliminate these incremental terms from the expression for delta E t. Now, to eliminate this, we make use of our generator stated circuit voltage equations. E d equal to minus R a I d plus L L I q minus psi q psi a q. E q is equal to minus R a I q minus L L I d minus psi a d. Now, these two equations were derived earlier and these equations represent the stated circuit direct and quadrature axis circuit equations. Okay. Therefore, what we do in this equation is that we give small perturbations, okay, and since these coefficients are constant R a, L L, these are constant quantities, okay, you just perturb them. Now, when you give this perturbation, you can write down delta E d equal to minus R a delta I d plus L 1 delta I q minus delta psi a q. Okay. Similarly, delta E q is equal to minus R a delta I q minus L L delta I d plus delta psi a d. That is, we get the equation for delta E d and delta E q in terms of delta I d, delta I q, delta psi a q and delta psi a d. Further, the expressions were derived or the equations were derived for deviation in delta ID, delta IQ, delta psi AQ, delta psi AD, and they were all expressed in terms of state variables. If you look into the equations derived earlier, right, then these 4 terms, that is the deviation in direct axis component of the current, quadrature axis current, then psi AQ and psi AD, they were all derived. Therefore, if I now substitute here in these expressions for these quantities in terms of state variables, and then you substitute delta ED and delta EQ in this equation, that is 18.61. Now, when we make these substitutions, then ultimately we can write down the expression for delta ET equal to a constant k phi delta delta plus k 6 delta psi f t. Now, this equation is the most important equation. That is, this change in terminal voltage of the generator can be expressed as k 5 delta delta plus k 6 delta psi f t. Okay. The expressions for k 5 and k 6 are derived, and they are written in the form k 5 is equal to EDO divided by ETO into minus R A into M 1 plus L 1 N 1 plus L A Q S N 1 plus EQO divided by ETO minus R A N 1 minus L 1 M 1 minus L A D S prime M 1. That is, if you see here the expression for k 5, right, then all the terms in this expression are known. They are function of the initial operating condition and the circuit parameters or the system parameters. Similarly, the expression for k 6 is written here, and k 6 is also function of operating condition and system parameters. Therefore, for any given operating condition, one can compute the constant k 5 and k 6. Now, after having completed the inclusion of excitation system model in the small perturbation model, before I talk about how this model is completed, let us first look here. If you see this portion of the model, this is the transfer function model. This portion of the model, it was derived earlier, where this was the delta EFD input signal. Okay. This portion here, the state variable delta psi FD, delta TE, delta omega r, delta delta, this was already derived. Now, right. Now, we add this equation, that is delta ET equal to k 5 delta delta plus k 6 delta psi FD. Right. Therefore, we add this summation point here in this block diagram, where one signal is coming as k 5 delta delta, another is k 6 delta psi FD, right. And what we get here is the delta ET, the change in terminal voltage of the generator. Now, we have also seen actually that the terminal voltage of the synchronous generator is sensed by putting a transducer. That is, we call actually the voltage sensor or voltage transducer. Okay. Now, we can represent this voltage sensor by a first order transfer function, that is 1 over 1 plus s times T r. This time constant T r is generally very small, right, small, and in some studies people ignore this time constant, or in some studies this can be included. There is absolutely no problem, only thing is the order of the model will increase when you include actually this transfer function. Okay. Now, you can see here that delta E t is the input to this transfer function, which is the transfer function of voltage sensor or voltage transducer. We will denote the output of this block by another state variable, we call it delta V. Okay. This delta V is now compared with delta V reference, which is small perturbation model. Okay. Delta V reference, that is this error delta V reference minus delta V is fed to the exciter. G E X S represents the transfer function of the exciter, and output of this exciter is delta E F D. Okay. Therefore, this transfer function model, right, is a complete transfer function model which accounts for change in field flux linkages, which accounts for change in terminal voltage of the synchronous generator, and which also includes the exciter transfer function model. Okay. Therefore, if I look at this transfer function model, we have two inputs here. One is the change in mechanical torque, delta T m is a input signal, then delta V reference is another input signal. I can change the reference voltage, right, if I want to regulate the terminal voltage. Okay. Similarly, if I want to change the mechanical output, you can change the position of the governor to change the mechanical input to the system, right. Now, for this system you can develop a complete state space model in the form x dot equal to x plus b u, and the state variables will be delta delta, delta omega r, delta psi f d, delta v and delta E f d. Now, in case this transfer function of this exciter is simplified, and sometimes we represent the exciter by a first order transfer function. Sometimes we represent this exciter by a constant gain only, right. If this is represented by a constant gain only, then delta E f d will not be a state variable. Okay. Therefore, I will suggest all of you to develop yourself a state space model of this system, okay, with input variables delta T m and delta V reference, and the state variables delta omega, delta delta, delta omega r, delta psi f d, okay, and delta v. Here delta E t is not a state variable. Okay. And the transfer function model which has been developed in the textbook is assuming that the exciter is a static excitation system and its time constant is negligible, so that you can represent the exciter by a gain K A only, right. Therefore, I suggest you to assume the exciter model as a a constant K A, okay, and then you develop the complete transfer function model of the system in the form of x dot equal to A x plus B u, and write down the A and B matrices. Now, here in the textbook, the textbook we are following, right. The model is developed assuming delta V reference equal to 0. Delta V reference is assumed to be equal to 0, right. That is, there is no change in the reference voltage, right. Now, in case this delta V reference is assumed to be 0, then there is only one input variable, right, and the model is developed here in this form. The delta EFD is equal to K A into minus delta V 1. You just see it here. This will come out to be straight away. This is delta, we call it delta V 1, delta V 1. Okay. This is K A, this is 0, but there is a minus sign attached here, right, and because of this there is a minus sign coming, and therefore, delta EFD is equal to minus delta V 1 into K A. Okay. And once you have this quantity delta EFD, you can write down the equation for P delta psi FD, because we have to write down the equation for the derivative of, or equation expressing the derivative of delta psi FD, right. And this can now be written as, you can easily see here when you write this expression. When you write this expression, delta psi FD can be written as K 3 divided by 1 plus S times T 3. Okay. What is the input to this? Input to this is delta E F D minus K 4 times delta. Okay. And this delta E F D we have just now seen is equal to minus K A times delta V 1, right. And when you make the simplifications and eliminate all those terms which are not the state variables, we can write down the equation for delta psi f d dot or d by dt of delta psi f d in the form A31 delta omega r plus A32 delta delta plus A33 delta psi f d plus A34 delta V 1. Okay. This is the equation which we can write down. And in this case, when you have assumed actually the exciter or represented the exciter by a constant K A or gain K A, right, the model which you get will be fourth order model, and the state variables will be delta delta, delta omega r, delta psi f d and delta V 1. They are the state variables, and you can write down the model in the complete form. Further, you can study the eigenvalue of the A matrix and analyze the stability of the system, because for any system the stability can be analyzed by analyzing the eigenvalue of the system matrix A, right. Now, I will just tell you the little historical development. This model, which has a 6 constants, it is popularly known as K1 K6 model, and it was originally developed in 1952 by Heffron Phillips. That is, it is called as, or it is known as Heffron Phillips model. there is K1, K6 model, also called Heffron Phillips model. This was developed, this was reported in a research paper, that is at that time it used to be AIEA, American Institution of Electrical Engineers, AIEA, in 1950. Then subsequently in 1969 the detailed studies were carried out by the two authors popularly known as DeMello and Charles Concordia, C. Concordia, and the results of their studies were reported in the IEEE transaction on power appreciation systems in the year 1969, and therefore, many times people refer to this model K1 K6 model as DeMello Concordia model, right. But originally it was developed by Heffron Phillips, and still actually it is known as the Heffron Phillips model, and this is the very important model which is used extensively for analyzing the small signal stability of a machine infinite bus system, because this model is basically for single machine infinite bus system. Similar models have been developed for a multi machine system also. Now, I will just skip over some of the transparencies. Now, we will analyze one very important aspect, that is what is the effect of AVR on synchronizing and damping torque components. We have now included the excitation system, right. Therefore, for once we have included the excitation system, right, we can either refer to this as effect of excitation system control, or we can refer that effect of AVR, automatic voltage regulator. Okay. Now, we will study the effect of this AVR by analyzing the synchronizing and damping torque components. Okay. Now, to obtain the synchronizing and damping torque components which are produced when the rotor is under steady state condition or when the rotor is oscillating with some frequency. That is, we will analyze again under two conditions. One is the system is under steady state operating condition, another is when the rotor is oscillating with some frequency. Okay. Now, to analyze this, again we come to the expression for delta psi f d, right. Now, the delta psi f d can be written as K 1 divided by 1 plus S times T 3 into minus K 4 delta delta, because our expression here was delta E f d minus K 4 delta delta. So, minus K 4 delta delta is written here, and we are writing now here the expression for delta E f d, that is minus G E x s or 1 plus S times T r multiplied by delta E t. This is delta E t, this K 5 delta delta plus K 6 delta psi f d. Okay. That is, if you again look at this expression, then what we are trying to do is that now we are trying to find out an expression for delta psi f d. Okay. Now, this delta psi f d we can write first as delta psi f d equal to this transfer function into delta E f d minus k 4 delta delta. Then this delta E f d is replaced by this transfer function g x into delta V 1. Okay. And then this delta V 1 can be replaced by this expression, this transfer function into delta E t. Okay. Now, with this things represented, we have represented all the things here, that is delta psi f d is equal to 1 upon 1 plus s times T 3 into minus k 4 delta delta minus G s divided by 1 plus s times T r, because we are not assuming that G s equal to k in the beginning, but for understanding and for simplicity we will replace G x by k later on. We are also taking the time constant of the voltage transducer. Okay. Therefore, this is the complete expression which is now written in terms of the state variables, because delta delta is a state variable, delta psi f d is state variable. Okay. Now, you rearrange the terms, so that delta psi f d terms come on one side and other terms come on the right hand side of the equation, right. Now, by rearranging, the expression looks like this: delta psi f d equal to minus k 3 into k 4 1 plus s times T r into closed plus k 5 G x s divided by s square T 3 T r plus s times T 3 plus T r plus 1 plus k 3 k 6 G e x s delta delta, right. Whereas I have told you just now that we are transferring all the terms, right, all the terms which are having delta psi f d on left hand side and remaining term on the right hand side. Right hand side terms will have delta delta. Okay. And then we write down the expression for delta psi f d as this transfer function into delta delta. This is exactly similar to what we did actually when we assumed the delta E f d equal to 0, right. But since now we are including the exciter or excitation system, the expression for delta psi f d becomes a slightly more complicated. Okay. But here this delta psi f d which we are writing down here, right, is now function of these constants. You can see all the constants which are coming in this picture except k 1. You have k 3, k 4, k 5, k 6, right. K 2 does not come in picture so far actually this delta psi f d is concerned, right. This function of these 4 parameters, it function of the transfer function of the exciter, is also the function of these constants like T r and so on. Therefore, I can say that delta t due to delta psi f d is equal to k 2 delta psi f d. Okay. That is the electromagnetic torque produced or air gap change in air gap torque. Change in air gap torque due to change in delta psi f d is equal to k 2 into delta psi f d, right, because we have seen that the total change in air gap torque is k 1 delta delta plus k 2 delta psi f d, right. Therefore, the air gap torque or change in air gap torque due to delta psi f d is equal to k 2 delta psi f d. Okay. Now, to illustrate what is the effect of AVR gain, we take this typical example where the constants of the model are given as K1 equal to 1.591, K2 equal to 1.5, K3 equal to 0.333, K4 equal to 1.8, T3 1.91, K5 is minus 0.12, K6 0.3. The time constant Tr is taken as 0.02, a small time constant. The exciter is represented by a gain Ka. Okay. Inertia constant H of the system is 3 and Kd equal to 0. In fact, these are the parameters of the complete system, right. Although, when we are trying to analyze the synchronizing torque coefficient produced due to delta psi fd or due to the AVR action, right, the H will not be required. Now, here I am trying to emphasize that knowingly we are taking K phi equal to a negative term. For any system, as the system loading changes, the K phi varies from positive to negative. That is, if you compute the value of K phi considering wide variation in loading condition, right, then the K phi is positive for light loading condition and K phi becomes negative when loading becomes high, that is heavy loading condition K phi is negative. Okay. Now, we have taken deliberately K phi equal to minus 0.12, a negative value. Now, with this parameters which we have assumed, first we will study the steady state synchronizing coefficient. Steady state synchronizing coefficient. That is, for obtaining the steady state synchronizing coefficient, what should we do? In this expression, we substitute S equal to 0. S equal to 0. When I substitute S equal to 0 in this expression, right, you will find actually that delta T due to delta psi fd is equal to 0.06 Ka minus 0.9 divided by 1 plus 0.1 Ka. That is, I have not substituted the value of Ka, I have expressed this torque in terms of AVR gain, okay, Ka. That is, delta T due to field flux changes or deviation in field flux linkage is written as 0.06 Ka minus 0.9 divided by 1 plus 0.1 Ka into delta. Okay. Now, if I take K equal to 0, K equal to 0 is a condition similar to constant field voltage. That is, when you apply constant field voltage, okay, it means we are not assuming the AVR action, that is K equal to 0. If you take K equal to 0, this quantity, that is the synchronizing torque coefficient due to delta psi fd is equal to minus 0.9. Okay. That is what we had seen earlier, that the for constant field voltage condition, right, the effect of armature reaction or demagnetization is to contribute negative synchronizing torque coefficient, therefore you get a negative one. Now, if you take K equal to 15, then this numerator becomes 0. For K equal to 15, you can easily see that 15 into 0.06 equal to 0.9. Therefore, if you take K equal to 15, then the contribution of delta psi fd to synchronizing torque coefficient becomes 0. Now, if I take K equal to 200, which is this case, the synchronizing torque coefficient becomes positive, that is 0.529, because the moment you put K equal to 200 and compute this expression, because this term is the synchronizing torque coefficient. Okay. Therefore, now the total synchronizing torque coefficient is equal to Ks is equal to K1 plus Ks delta psi f d, right, because K1 is, we have assumed the value of K1 equal to how much 1.591. Therefore, if I substitute actually K1 equal to 1.591 plus 0.529, you will get 2.12, right. That is when K5 is negative, K5 is negative, K is taken equal to 200, we find that the net synchronizing torque coefficient increases, it becomes 2.12 as compared to 1.59. Okay. Now, you and there is under steady state condition, it does not contribute anything to damping torque coefficient, because in this expression, right, what we are getting is that the torque is directly proportional to delta delta. Now, you consider the damping and synchronizing torque components at rotor oscillation frequency. Okay. Now, we again start with this expression, right. In this expression, we substitute the values of all the constants, and we will substitute the value of S equal to S as j times 10. A typical value is put here, S equal to j times 10. Perhaps this value is chosen to simplify the calculations. Okay. Now, if you make these substitutions, delta T due to delta psi f d again comes out to be 11.1 minus j times 0.18 divided by 17.18 plus j times 19.3 delta delta. Okay. Therefore, what you see here that this comes out to be the coefficient of delta delta is a complex number. You rationalize this expression, find out separate the real and imaginary parts, then you can write this equation in the form 0.2804 delta delta minus 0.3255 j delta delta. Okay. Therefore, now you can easily see that this is the synchronizing torque coefficient, right, and this is positive, while the damping torque coefficient in this particular case is to be computed as yet. What is to be done here is that in this expression, what you do is we have this relationship, we have the important relationship, that is delta delta equal to omega naught divided by S delta omega r. Okay. Now, here in this equation, if I put S equal to j omega, right, then I will have the term j times delta delta equal to omega naught omega delta omega r, right, and this expression, that is I can write down delta T e due to delta psi f d equal to 0.2804 delta delta, okay, minus 0.3255 omega naught divided by omega delta omega r. Okay. Omega naught is in this particular case 377, it is 60 hertz system, and omega is taken to be equal to 10. Okay. Therefore, this coefficient is the coefficient of delta omega r, right. Therefore, this is the total damping torque component, and this term 0.3255 into omega naught by omega becomes the damping torque coefficient, right. The damping torque coefficient is computed here and it comes out to be equal to minus 12.27. Okay. The important conclusion which we draw from this discussion is that when k phi is negative, right, if k is taken around 200, right, it contributes to negative synchronizing torque coefficient, it contributes to positive synchronizing torque coefficient and negative damping torque. Okay. With this, let me conclude that we have developed the complete transfer function model, that is the Halpern-Phillips transfer function model for a single machine infinite bus system, and we have also analyzed the effect of AVR on synchronizing and damping torque coefficient.